I'm Beata Szydłowska, and I'm from Heidelberg University right now. I used to be at Trinity College Dublin, so most of the work I will show would actually come from Trinity College Dublin because I moved to Heidelberg just 3-4 months ago, so I'm just starting there. And I will tell you about an incredible world beyond graphene. So we'll be talking about nano devices. I'm not an organic chemist, I'm more of a physical chemist going towards physics, so this talk will be entirely different, I think. And the nano devices are all the tiny functional stuff which is made of the nanomaterials, but the ones I would talk the most about are those made of the things which you have. So the very, very simple approaches, like what you have in kitchen, in your kids' drawers, or in the office. So it would be nice to know what this nanoscience is. And all my work is around the nanoscience. And there's loads of attention about it in past 15, maybe 20 years in science in general. So when we talk about nanoscience, we think about anything what is small. And when we think about small, it's actually in nano, so nano dimension. And when we talk about nano dimension, we need to know how small actually it is. So for anything which is nano, at least one dimension of this object must be in the range of 1 to 100 nanometers. And just so we are all clear, 1 nanometer is 1 millionth of meters, so it's really, really small. And people know it from a very long time ago that when some objects, some materials get small enough, their properties change entirely. So that's nothing new, but I will base my work on it. So we all know what I'm going to talk about, and I'll start with the question. So did any of you have heard about graphene? Okay, I see some people did, some haven't, or maybe are too shy to say they actually did, but that's not a problem. So if you haven't heard about graphene, you must have heard about diamonds or graphite. So those are carbon allotropes. And as you can see here, and as we all know them, they are very different from each other, despite of the fact they are all made just of carbon. So they have totally different properties, and they behave differently. And graphene is another allotrope of carbon. It's just built up of carbon atoms. So here you can see the general structure of it. And these carbon atoms, so the spheres on the image, they are arranged in a honeycomb-shaped lattice. And actually, even those of you who didn't say that they know what graphene is, I know you all have an experience with graphene, actually, because graphene is what we have on the paper when we use the pencil. So when you write whatever you write with use of a pencil, the trace you leave would be graphene, or maybe not exactly graphene, but something very, very close to it. So it will have about 1 atom thickness. So just imagine, you can do science only with a pen and paper. That's great. So going further, to help you imagine how it actually looked like, you can think of graphene sheet, so 1 piece of graphene, as of a cornflake. So it's actually very, very similar to the cornflake. It has folds and has some wrinkles, and its shape is almost exactly the same. It's just downsized to the nanoscale, as you said before. So this is a little bit more accurate representation of graphene sheet, which is also called graphene flake. That's why this correlation with cornflakes. And graphene is such a great material that in 2010, so not that long time ago, it was awarded a Nobel Prize. So the discovery of graphene was awarded a Nobel Prize in chemistry for groundbreaking experiments regarding two-dimensional material graphene. That prize went to 2 scientists from Manchester, Andrew Game and Konstantin Novoselov, and people believed that graphene is such a wonder material, which would have ability to revolutionize the world we know right now. And we still hope for that. And that's due to amazing properties of graphene, which changed a lot when it was downsized from being a carbon to the graphene. So it's 100 times stronger than steel, or it's very light and rigid, so might have loads of applications just in the everyday life devices. And as I said, the Nobel Prize was awarded in 2010, and usually it takes a long time from the discovery to the prize being awarded. And this time, it was such an impactful discovery that it took only 6 years between the discovery, which was in 2004, and the Nobel Prize. So that was separated in 2004 with the use of a Scotch tape. So something which, again, every one of us have at home, at school, in the office, so something very, very accessible. And this brings the message that to change the world, we don't need any fancy equipment. Of course, we need being scientists, but in general, we need a good idea. And if something is simple, it is possible. In my work, I don't use a Scotch tape. I actually use liquid phase exfoliation. And again, just to make it easier to understand, we can compare graphite, so the black one here, to the sandwich cake. Maybe some of you know this cake, so it's made of layers of a dough, put one on the other one, and the graphite is very similar. So in the liquid phase exfoliation, we take graphite, so the one which we said can be found in pencils, and we put it in some liquids like water or maybe organic solvent for organic chemists, and then we provide energy. And when the sufficient amount of energy is provided, then we just blow apart all the sheets, and we end up with millions of nanosheets of graphene in the dispersion. And in the lab, it can be done, again, with something what you find in the kitchen this time, so with a kitchen blender. So to make this fancy graphene, you need kitchen blender, you need water. It can be any water which you can buy in the food store. You need a graphite, so could be taken from the pencils, and you need some stabilizer. So in this case, if we go very low cost and for approachable, it's a fair liquid, so that's the washing soap for the dishes in Ireland. I don't know what's actually used in Germany because I'm here so short. But this one acts as a stabilizer, as I say. So when you exfoliate the sheet and when there's nothing to stabilize them, then we have a problem because they will come back together. And, well, that's not what we want, right? So here it's like an example of a real sheet. So you have imagined it as a cornflake, then you saw some approximation, and that's how it looked like under the TEM, so transmission electron microscopy. And those are actually both exactly the same flakes. I don't know why I put two same images, but I did. So you can see that the length of this sheet is about 2 microns here, and the width would be about 800 nanometers. And still, they are just one atom thick. So very small, and we can observe some wrinkles and folds. So for me, they just look beautiful. Okay, we've learned about graphene, but there's not only graphene. Graphene was like a start of this fancy adventure, and there's like a whole 2D family. And in this family, I just put the picture of many vials. Each of them consists different 2D materials, so some material sized down to the nanoscale again, with use of the same method which I presented to you. And those metals represent variety of different properties. So they might be conductors, semiconductors, or insulators. And just now I've named 3 main building blocks of electronics. What does it mean for us? Just as an example, I will show you 3 of them. So graphene, which we all know by now, which is a conductor, tungsten disulfide, which will represent semiconductors, and the boron nitride, which is an insulator. All of them are two-dimensional, all of them are very flat. They're one atom thick, but they're built with different atoms. So graphene out of carbon, tungsten disulfide out of tungsten and sulfide, and the boron nitride out of boron and nitride. And having them ready, three main building blocks of electronics, we decided to make a transistor, which is the smallest part of any electronic device we know. And this was made, again, with something very accessible. So the inkjet printer of an old type. And we took the cartridges. We just emptied them and we replaced inks with boron nitride, tungsten disulfide, and graphene. And using those as inks, we have printed the transistors. So those are very quick, very easy to make, maybe still not perfect, but come on, we've worked many, many years on silicon devices, so we still have the time to improve. And the great advantage of it is that they can be printed on any surface. So it can be flexible, it can be very flat, it can be waterproof or not, so it just depends on where you would like to use it. The other application which is possible and which is very nice to play with are the strain sensors. So we've took, again, something simple, just the rubber bands, those which you can get in pharmacy or paper store, and we soak them in NMP. So rubber band is made of polymer, and when it's soaked in the NMP, it swells a lot. So you can see that the size of the rubber band in the vial, it's like enlarged. And then when it's swelled, the pores of the polymer opens. And we soak it back in the dispersion of graphene, which is black. That's why the last image is actually black. So then the graphene can go inside the pores. So we end up with a rubber band infused with graphene sheets. And here, I think the only scientific plots I have in my talk. So we made a couple of experiments. So the first one is when we put the rubber band around the finger, and we were just moving with the finger, and then below you can see the difference in resistance, so how this band acts as a sensor. The second one, so the C image, is where we put the rubber band on the arm, and when you were moving your arm, again, you could see the difference in the resistance. And third picture, the rubber band is put on the throat, and a friend of mine, Connor, he was repeatedly saying word graphene. So we see how the resistance change when he speaks. So it can be also a speech sensor, so a microphone, basically. And this is being used now for commercial reasons, for a breathing sensor. So there's a problem commonly known for children that they have like problems with breathing at night. And then it's very difficult to put the proper sensor because the newborns are very, very small. And when we want to wire them, it's just dangerous because they can tangle with those wires, and we want to avoid it. So people are starting to work on breath sensor made of just this rubber bands, which would be much more safe and also cheap because, come on, like it must be cheap so it's available to like everybody. And the last option are the elastic sensors. So that's the newest part of our work. It's just from the end of it's actually from this year, when we put the graphene into the silly putty, so to plastiline. And when this is infused with graphene, it creates the most sensitive sensor known till now. It's that much sensitive that you can sense the single step of a spider on it. So I know it might not be right, but we have caught some spiders, And we force them to walk through our graphene, and it actually works perfectly fine. So, and they are safe. We just release them to the nature afterwards. So that's just amazing. And you can use it for science, but also for science education, which is very important as well for the future generations. So you can let the children to play with it and to learn some physics behind it. And just to conclude, I would like to say that applications are everywhere, and they can be made with very simple tools based on the knowledge we already got in our labs with our fancy equipment, and it's only limited by human imagination. So just by our imagination, and I strongly believe that our imagination is limitless, and we can make a great deal out of it. Now I would like to thank you, a few people. So Professor Jonathan Coleman, who was my supervisor at Trinity College Dublin during my PhD thesis, as well as, so it's this guy in the middle, and Professor Werner Blau, who is my co-supervisor. He's a real physicist, nonlinear optics physicist, as well as Dr. Claudia Bacchus, who helped me a lot and who was my scientific aunt through the whole time. And I also would like to thank you for your attention, and I hope you learned something today.